Okay, so where we left off was we were just starting to introduce this algorithm from Nicholas Metropolis that was designed to use computation. So this is an algorithm from early 50s. Computers are starting to be used to understand the properties of matter, physics. They've just come out of very successful, arguably, uses of computational methods to help them design things like nuclear weapons and so on. And so Metropolis works with a group of colleagues and publishes a paper that was titled Equations of State Calculations by Fast Computing Machines. And this is by Metropolis et al., 1953. And what Metropolis is saying is now that we have computers and things like that, we can now start imagining models of matter where we actually could simulate a bunch of these microstates in complex configurations. And so if we start simulating these things, or if we have some sort of mathematical or computational models or whatever, we can now start using computers to start numerically calculating interesting quantities for us. And so these equations of state, I'm going to highlight that. What is meant by this is basically, functions of microstates. And so you have a complex configuration of a system. This is some complex, high-dimensional configuration of a system. And this here is some macroscopic property. So like pressure or whatever. And given that the microstates can be in one of exist across a distribution of microstates, then you might ask questions like, for this model that we built with all these microstates, then what is the expected value? So I can say, what is the expected value of this function f over the distribution, which I'll call little f, across microstates. And of course, mathematically, we can write that. We know that it's just, the integral across these microstates, I'll say states, of the function at each state times the density, the probability density at that state, times a little differential state here. And this integral could be taken across multiple dimensions or whatever. And so this is how we would mathematically calculate that. But realistically, this function, this big function f, might be very difficult to calculate. These, just in general, these states are such high dimensions that numerically speaking, this would be very difficult to solve analytically, like by hand. So the simple way to approximate this, coming out of successes, again, coming out of the nuclear age in the 1940s and whatever, was to use Monte Carlo sampling. So one idea was to use Monte Carlo sampling. Maybe I'll move that up just a little bit. And then so in Monte Carlo sampling, the idea was that this integral could be approximated by, so the expected value of f over the microstates, over this little function f, could be approximated by a ratio f of sample 1 times little f of sample 1 plus all the way up to f at sample m times little f of sample m divided by m for m samples. I'll say m uniformly drawn samples microstate samples. So this is a simple numerical method to approximate this integral. You just say, over all the microstates, I'm going to go out there and I'm just going to sample them uniformly. Here's all the different possible ways that this piece of matter could be configured at a micro scale, from position, momentum, or whatever. And I don't know how likely each one of those things are, so I'm going to take each one of those microstates. So here's a sample microstate, S1, and I am going to plug that microstate S1 into the function that I'm trying to take the average of, big F. I'm going to scale the whole thing by the density function, which represents sort of how likely it is that I would actually get that microstate in this piece of matter, this hunk of matter or whatever. And then I'd sum up over m of those and divide by m, and that simple average, that arithmetic mean, if I have a very large m, is going to approximate this integral that I actually want up here. But in order for that to happen, this has to be a very large m. So this, in theory, could work, but in order to get convergence, you need a really, really large m. So how many people have done in some class, whatever, an example of Monte Carlo sampling? Like maybe you estimated pi by drawing random numbers. Does this sound familiar to anybody? So like that's like a common thing you can do in Monte Carlo sampling is you can, so, you know, as an example in Monte Carlo, so the quick background, so example, I'll say simple example. Of Monte Carlo sampling. We know that if you had a circle, so if let's say I'll put a square here. Oh, I'm going to try to draw a square. And then if I were to put a circle inside that square, something like that, then I know that, you know, the area, the circle area is, if I call this distance r from the center of the circle, the radius, I know the circle area is pi r squared. And I guess I meant to write that in purple, but oh well. And I know that the square area is equal to 2r squared or 4r squared. Then I know that if I randomly threw a dart at this dartboard, then the probability of a dart hitting circle would just be the ratio of the two areas. So there would just be pi r squared divided by 4r squared or pi over 4. So what does that have to do with anything? Well, so I know that in theory, if you just randomly drew, you know, threw darts, so if you uniformly drew random numbers in x and y, so if I draw x uniformly distributed from you know, minus r to r, and y uniformly distributed from minus r to r, if I randomly draw those and then count, then I could ask how many inside circle So in other words, I could calculate, well, does x squared plus y squared, is it less than or equal to r squared? I count how many meet this predicate, meet this condition here, and divide by how many I actually drew. So if I have the count inside circle divided by total count, then this thing over time, if I draw lots and lots and lots of samples, will approximate pi over 4. This is just like the simple introduction to Monte Carlo sampling, like the first experiment you have students do, like an undergraduate stochastic simulation course or whatever, something like that, or even a numerical methods course. And you can try this. You can go into your favorite spreadsheet program or MATLAB or Python or whatever and draw 1,000 random numbers. You could draw 1,000 random numbers for X, 1,000 random numbers for Y. Ask how many of them land inside the radius, and then divide by 1,000, and you should get an approximation for pi over 4. And if you multiply that thing by 4, you'll get an approximation for pi. So this is one of the many ways you can use Monte Carlo sampling to do crazy things like estimating pi, just by drawing random numbers. I didn't actually have to draw a real circle or anything like that, just mathematically, because the probability involves pi, I can go from sampling to probability, and the pi pops out of the sampling then, because in the limit, I should expect this thing to be shaped by pi. So it's a way of approximating pi. That is simple Monte Carlo sampling. All right, so that's basically what you're doing over here with this thing, is that you're drawing lots and lots of samples, and you're not approximating pi, you're approximating this integral. But this approximating pi, you can do this pretty well out to several digits with 1,000, maybe 10,000 rows, or 10,000 samples. And so 10,000 X's and 10,000 Y's, you can get pi out to, I don't know, 3 or 4 digits. It's pretty good. But in order to get this, you would need a huge number here. So although this works in theory, because the state space, the microstate space, is so gigantic, then this ends up being very difficult to actually work in practice. And it requires so many samples that it's not really much of an advantage. So you end up still taking, especially back in 1953, it just takes forever to do this calculation. So Metropolis recognized that something better was needed if they really wanted to advance into kind of this, using fast computing machines, computers in physical chemistry. They needed something better. And so that's where they came up with this Metropolis algorithm. So what was Metropolis's insight? Well, are there any questions about that, about the Monte Carlo sampling in general, or the basic idea here? Any questions online? Okay. All right, so Metropolis said, well, actually, the problem here is that we're sampling uniformly from all microstates. And so it is equally likely for us to hit a very unlikely microstate as it is a very likely microstate. And so we're going to we're going to go through the process of drawing a microstate here, which the density might be near 0. So we're going to draw maybe a bunch of samples that are going to end up being wasted. So it'd be nice if we could somehow bias our sampling so that really only sampling from microstates that are likely to actually be occur in the material. So wouldn't it be great if instead of sampling uniformly from all microstates, we could just sample from the Boltzmann distribution, the maximal entropy distribution, because we know at thermal equilibrium, by thermal equilibrium, I mean, this chair is all at one temperature, So if I want to know what's going on inside this chair, I approximate it as all being at one temperature. And at thermal equilibrium, we would expect that its microstates would be drawn from a Boltzmann distribution for that particular temperature. And so if I could just draw microstates from a Boltzmann distribution, maybe I can actually make this approximation with far fewer samples. And so what Metropolis realized is that if, so the alternative for estimating the expected value of our equation of state under that density, the alternative is that, this expected value is actually approximated by the arithmetic mean without the densities when samples are from F itself. In other words, if you've ever taken a course on measure theory, sometimes people in grad school do that, then you learn about the whatever, the recon Nikodym derivatives and things like that. I mean, the idea here is that the integral you want to take isn't over the uniform space. The integral you want to take is over the space where microstates are distributed in a more clustered way according to this distribution F. And so when you're taking this integral back here and you're putting this density in, this density is a correction factor for the fact that you're viewing space in you should be viewing space in a biased way. These microstates aren't equivalent. So an integral without a density function there sort of says every microstate that you're integrating over is equally special. And in reality, they're not equally special. So we create these probability density functions that sort of say, well, even though in theory, you can go over the entire real line if you're integrating over a real line or whatever, in reality, some locations are more privileged than others, and that's why we amplify them with some densities and we suppress others with other densities. And so the idea is if you have a way to sample from space in a way that really weights the space by the likelihood of them occurring, you don't need those density correction factors up here. And so this is the nuance here. So this is, I just want to emphasize here, we are not sampling uniformly. We are sampling according to distribution F. And at thermal equilibrium, distribution F is a Boltzmann distribution, which is the max entropy distribution at a given temperature. So that's really what Metropolis wanted to do, is to say, if we can just actually simulate a Boltzmann distribution on a computer, we can ask the computer to not draw microstates randomly. We could draw it not at highest entropy uniformly. We can actually have it draw it in a realistic way where microstates that are more energetically favorable occur more often. Microstates that are less energetically favorable occur less often. And if we draw in this biased way, that is according to the Boltzmann distribution, we can actually then use this approximation up here, this numerical approximation, and we will need a much smaller, so requires smaller m for convergence. All right, so that's what Metropolis wanted to do, is in the end, he really just wanted to say, how do we sample from the Boltzmann distribution? Because if we could sample from the Boltzmann distribution, then we could approximate these equations of state using far fewer samples. All right, so I see a question online. Can you use the can you explain the same using the circle square analogy? It's kind of difficult to understand why density is dropped. Yeah, I think I can. I mean, I think there's two ways for me to do this. And before I go the one direction, let me look back and see if I want to go a different direction here. So the idea here is that, so in the circle, the square example here, what we're saying is that we're going to sample uniformly. And then we're going, so by sampling uniformly, what that's going to mean is that sometimes you sample outside the circle, and you're effectively going to assign that sample a 0. And sometimes you're going to sample inside the circle, and you're going to assign that sample a 1. And you're going to do that over and over and over again, 0s and 1s. And then after assigning all those 0s and 1s, then you're just going to take the average of these. And so then here, the average of 0s and 1s will be pi over 4. So in this context, the probability density that we see here is just the mapping of the sample outcome to a 0 or a sample outcome to a 1. So what we're saying here is that this is saying we're going to count all samples, but we're going to weight the samples by how likely they are. And in this Monte Carlo example here, we're saying that the samples inside the circle are 100% likely. The samples outside the circle are 0% likely. So it's an extreme case where, another way I could put that is I could say the square, I could say F square is equal to 0 and F circle is equal to 1. And so when I scale, if all the samples are 1, and then I multiply them by their Fs, then that's going to mask out all the samples outside the circle, so that when I then divide the numerator, which sums up all the weighted ones, by the total number of samples, I get pi over 4. So that's kind of, this is sort of playing the role, sort of, say, role of F. Is the 0 and the 1. Okay, so that's kind of the idea here. Now, you could say, well, what if I could manage to just draw samples only from the circle? And so that's kind of the magic here, is to say that here we don't know how to draw samples from just the circle. We do know how to draw samples from the square. So we draw samples from the whole square, and then we weight those samples by their kind of density score. And that's what gives us the Monte Carlo average that allows us to go to pi over 4. And so the trick here would be to say that, well, if there was a way for us to sample from the circle, then maybe there would be a way for us to estimate this pi over 4 with less wasted samples. We have less, because it is kind of wasted that you have to sample from outside the circle. So this whole thing goes into what if you want to look up more about this, this fits under the category of importance sampling. And to link this back to computer science and things like that, those of you who work in probabilistic model checking, or have thought about you working probabilistic model checking, or in counterexample generalization or counterexample generation and things like that, this even links to software engineering, then this also plays a role, is that how do we manage to sample from possible states in a way that sort of wastes less time in the computational method. So what is importance sampling? So importance sampling is this idea that any integral, or if I think about taking an expected value, so if I'm taking the expected value of like g of x times its density f of x, so I'm taking this integral over all of x, well, I know that this here can be approximated by, and wait for it here, this looks normal at first, but the sum of samples of x, g of I, and then multiplied by the original density over some proposal density here. And this here we refer to as a likelihood ratio. And so we say that F is desired distribution, but then P is our sampling distribution. And P and F have same support. So basically that just means that P and F are non-zero in all the same places. So there's no place where P is 0 and F is non-zero, and vice versa. They have the same support, but they aren't necessarily the same distribution. And so we refer to P sometimes as the proposal distribution. And I'll use that term because it'll come up later when we get back on track here. So the idea here, if you think about what, or another way I could say this is if you like the more continuous side of things, an integral of g of x times f of x dx is the same as an integral of g of x times, so if this integral is taken over the f distribution, is that the way I want to say this, then this other integral, no, I'll do it this way. Or no, sorry, I want to do that slightly different way of, yeah, okay, we'll do it this way. All right, yes, this is what I wanted. Okay, so I hope you can agree that the integral on the left is equivalent to the integral on the right. I just added this g of x over g of x right here. If that's the case, then I can rearrange this as this thing here. I just rearranged it. I just moved it around. So what, if you look at this thing here is the expected value of g over the distribution f. But this thing over here is the expected value of g times f over g taken over the distribution g, but they're equivalent. So I know that it kind of depends on how far back you've worked in probabilistic modeling and all that, but maybe the last time you take a probability course or whatever, and maybe this starts to come back to you a little bit here, but the idea here is that I can view the expected value of a function over one distribution as the expected value of that same function times a likelihood ratio over another distribution, and they're equivalent. So the idea here is that drawing uniform samples of this, drawing uniform samples of x scaled by f is like kind of the one way that we can learn that we can approximate this. But we can also say that, well, that would be kind of similar to drawing uniform samples scaled by this weird thing. So uniform samples where you're multiplying everything by this. And so, but we know though that this thing here is equivalent to this down here, which tells us that if we can just draw, samples from G, it allows us to, it gives us an alternative way to calculate the exact same thing. And so this is, again, I said there's like 2 or 3 different ways I could say this. I don't know which one's going to resonate better with different people, but this all is exactly the same as the circle case. Is this, all this Metropolis sampling that I'm going to get to here is all examples of this importance sampling, where the idea here is that you can either sample uniformly and scale by some density, or you can sample with a different distribution and scale by this likelihood ratio. And so if your likelihood ratio is uniform, so this proposal distribution, it could be uniform. And if it's uniform, then it's just a constant. So the probability is going to be the same across all microstates. But it could also be something else. So this would be constant P. And this would be variable P. And so usually we draw from a uniform distribution and we don't think about the importance sampling because it all factors out, because if you have this constant down here just ends up falling out of this and ends up kind of joining with the constants that are out here. But importance sampling allows us to sample from other distributions, potentially with fewer samples. And so, I don't know if this is necessarily helping, but I'm hoping it's kind of pointing in the right direction. And I guess I just generally say that for more information, check this out. And then that also, just generally Monte Carlo as well. So I don't know if that helps online. I didn't see any follow-up questions there, but I'm hoping at least the importance sampling reference and the kind of conceptualization of this sample being weighted by 0, this sample being weighted by 1, and then the weighted samples being the things that are being summed up here. I guess I could even write that here, where this is equivalent to, sample, 1 times F square plus 1 times F circle plus that whole thing divided by total count. And then these weights up here will end up being the count inside circle. All right, so I don't know if that mucked things up more or if that's at least helped, but I'm trying to say there is a mathematical foundation for all of this. And fundamentally, it relates to this property down here, where you can translate one density to another density through a likelihood ratio, so that you can take an expected value over a different density if you just scale the thing you're taking the expected value of by that likelihood ratio. And that's all we're doing. And so by switching distributions, by going from our desired distribution to a proposal distribution, the hope is that we can actually reduce the number of samples needed to approximate this thing, and in doing so, approximate this thing, because they're equivalent. Okay, so that's kind of background on Monte Carlo and importance sampling. So what did Metropolis do? Well, Metropolis, going back to there, Metropolis said, well, how do we sample from Boltzmann? So the Boltzmann, this is our desired proposal distribution. So if we can sample from the Boltzmann, then we don't have to, we can stop drawing samples outside the circle. We can sort of focus on trying, we want to concentrate our samples inside the circle and not outside the circle. That's what Boltzmann, what's what he's trying to do here by sampling from the Boltzmann. And so the algorithm that kind of came up here was to say, so this is the Metropolis algorithm. it's sort of been come to know. And the idea here is we choose a random microstate, just anyone. And then we move to a different microstate. Not move, I'm going to say we choose a random microstate, and then we choose a nearby microstate. And I'll just say it's perturbed by random amount. So then the idea here is we're trying to decide, do we stick with our original microstate or do we go to the new one? That's kind of the goal here. And then we're going to iterate. And so if new microstate is at lower energy, we're going to say we're going to accept the new microstate as a sample, and then we repeat. So then we go up and we repeat, we'll say from number 2. Alternatively, if new microstate is at higher energy, then we accept with probability equal to the exponential times negative the difference in energy divided by KT. Then we say, or take old sample otherwise. And then we repeat. Okay, so this is the Metropolis algorithm. The idea kind of here is that you assume that you're at so the ground state is the microstate at lowest potential energy. You can't go any lower. It is sitting on the ground. And you sort of say, maybe I got lucky and I chose the ground state. And so if I chose the ground state, that's interesting. But if I end up going to a microstate, which after I calculate its energy, find out it's a lower energy, then I say, oh, I'm not at the ground state. So I am going to then immediately go to the next one and assume that's going to the ground state. Otherwise, if I'm at the ground state, so I've managed to choose a microstate that's above me, then I have to think about, well, what is the probability conditioned on me being in this state? What is the probability distribution of all the microstates that are above me? And if I remember, I assume we're at max entropy. And so I assume that there's a Boltzmann distribution of microstates. And if I sort of think about what's the conditional probability of moving from one microstate to one that's of a higher energy, it's this. This is just the ratio of those two Boltzmann factors, where it's the Boltzmann, the probability at the higher energy microstate divided by the Boltzmann probability at the lower energy microstate. And it ends up being exactly this thing right here. So this ends up giving me a probability that allows me to jump to a higher state, but where the higher and higher and higher you go up, the least likely it is for you to accept that. So I'm proposing new microstates. If they're at lower energy, I always take them. If they're at higher energy, I take them based on how far away they are. If they're really high, I'm not going to take that jump. I'm going to stick with my current position. If they're close to me, it's possible that I'll take that jump. And so, so coming out of this, we don't think about this converging. We do sometimes think about something called a mixing time. So there might be a small transient period where we throw away samples from this. So we wait, so this will generate, I'll mention this here, generates a sequence of never-ending samples. So that's, if you can read that, it's supposed to say never-ending. So we wait for this so-called mixing time. So we wait for a certain amount of time. And so, but you just basically throw away the first couple hundred samples or whatever. And then after that, we just take every sample that this thing produces, which will either come out of step 3 or step 4. This thing's going to keep shooting out samples, and we take those samples. If you were to take a histogram of the samples that came out of that, so if we were to sort of draw a thing here, so this is the energy of microstates produced by the Metropolis algorithm. And this would be the, say, frequency distribution. So this is a histogram. You would get basically an exponential. So in other words, you get a Boltzmann distribution for temperature T. So that's the beauty of this thing, is that it keeps producing samples that over time just fill out this histogram. So you will get samples, this here be very frequent samples, and then this is occasional, sometimes samples, and then sort of never samples. And so it is a it's a sampler, but we have to think about it kind of operating over time, and it's kind of constantly moving from one thing. If you notice, it has an internal state. So this Metropolis algorithm is itself, you can think of it as a Markov chain, where it has some internal state, and there's always some probability that it's going to jump to some other state, and then jump back to another state, jump forward and back and forward. And we're just watching the Markov chain move. And so these are outputs. So up here, these are outputs from an observable Markov chain. Okay, so that's the Metropolis algorithm. This was a way that Metropolis used to be able to draw microstates whose energy would converge to the Boltzmann distribution. And so he could then say, well, okay, we want to like draw 1,000 samples. So he just would let this thing run, and it would generate 1,000 microstates. And then those 1,000 microstates, he would evaluate his equation of state. He'd evaluate, and then he'd just sum up. He'd take the average of those equations of states divided by 1,000, and that would be his estimate of the integral, estimate of the expected value he was trying to take. So that's the Metropolis algorithm, which is just a way of sampling from Boltzmann, which can then simplify sampling these numbers. All right, so let me let that sink in. I see a question or two online. So there's a question about what do we have multiple objectives? So we haven't got to optimization yet. So we are about to apply this to optimization, but this metaheuristic that's going to be formed from this is focused just on single objective optimization here. So you could extend this to multiple objectives, and I think you can find that people have done those sorts of things, but simulated annealing is most kind of directly tied to single objective optimization, but we haven't quite gotten there yet. We have to turn this into something more generic in order for us to start using it in our optimization cases. So we're about to get to that. There is a question, delta E in the probability is for higher energy is calculated as the difference between the higher energy and the random microstates energy. If not, please explain. And so then there's a clarification there. I can just write this down. So when I said delta E, I can just clarify that delta E is equal of the energy of the new micro state minus the energy of the old microstate. And so you can see here that if delta E is extremely large, then this thing will be extremely small. If delta E is extremely small, then this thing will approach 1. So that's what's going on here with that. And so this is with probability means that algorithmically, you would probably draw a uniform random number between 0 and 1, and you would compare that uniform random number to this threshold. And if that uniform random number you drew was less than that threshold, you accept it. So if I wanted to write that out, if that's helpful, I draw a uniform number from 0 to 1, and then I ask, does the uniform number, is it less than or equal to that exponential? And then if so if yes, accept, no, keep old. All right, any other questions about the Metropolis algorithm? The Boltzmann sampler. Okay, so that stuck around for quite a while, and then a little bit later, I think in the 70s actually, another researcher named Hastings realized that you could do more with this approach than just sampling from the Boltzmann. He realized you could sample from any distribution this way. And so a little bit later, Hastings realizes Metropolis alg can be generalized to any distribution. Not just Boltzmann. And so that, what was being published by that is now what we frequently call the Metropolis Hastings algorithm. I'll call it just MH. And so the way Metropolis Hastings work is, this will be a slightly different than I think the format I wrote out the Metropolis here, but I generate an arbitrary X naught and some proposal density which I'll call G y given x. And what is this proposal density? This is often taken to be, I'll maybe write it on the side here. Often, this is just x plus a normal distribution with zero mean and a specified amount of variance. So maybe I'll put that in little brackets here. All right, so basically in step one, I draw a point and I set up a proposal density, which is just a way to get from my original point to some new point. So just like in step one and step two of the Metropolis algorithm, I drew a point and then I drew a point kind of nearby, some random point. Well, this is his way of just formalizing that. So here is my current point. Here is a way to, given the current point, generate a new point nearby, where nearby is parameterized by the amount of variance in this distribution. Okay, so then, so basically this is setting up something here which hopefully looks like a random walk. All right, step two, generate our next candidate by sampling from that proposal distribution. So generate next candidate by sampling from G of y given x, our previous x. So we just draw from that proposal distribution. And then this is kind of the generalized part here. We're going to calculate an acceptance ratio alpha is equal to f of y, and that's, so we're going to call this up here y, f of y divided by f of x and so where f is desired distribution. So in Metropolis, f was just the Boltzmann distribution. So now we can make f anything, any distribution that we would like to sample from. And then if alpha is greater than 1, I guess I could say greater than equal to 1, except y, and go to back to step number 2 with y as x. So I guess I will say y gets put into x. And then otherwise, if alpha is less than 1, you might guess we're going to accept with probability equal to alpha. With probability alpha, and then go to number 2. The same as we did, so same as Metropolis. Okay. So, you know, with respect to x and y. So whether we take x or take y. So this is Metropolis Hastings. It's just a simple extension of Metropolis where you can use a different distribution here. And this allows you to sample from really any distribution you want, but it's sample in this sequential way where you're effectively building a Markov chain where the transition probabilities cause you to move from one state to another, such that when you then marginalize over all the states that you get out of the whole thing, when you actually look at the distribution of states that are traveled by the Markov chain, then the residence times in those states will be according to this distribution here. So this is just a Markov chain sampler of distro F. So if you've heard of Markov chain Monte Carlo methods, all those are based on is this idea that we're going to do Monte Carlo sampling, but we are going to do Monte Carlo sampling sort of sequentially using a Markov chain to be drawing points that will then go into the Monte Carlo method. So we'll go into the numerical averaging coming from the sampling process. And so that's where the Markov chain comes from. And so the Metropolis Hastings algorithm was really the kind of first major MCMC method. So this is like, I guess I could just put this here. This was sort of the first MCMC is this guy right here. Okay, so that's kind of our generalization. Now, are there questions about this basic thing? And it's just a simple generalization of Metropolis with, instead of using the Boltzmann, you use any distribution. Make sure there's nothing new online here. All right. Okay, so this MCMC method. So basically, this idea of sampling this way, there's good and bad aspects of it. So the positive about this is it's so that it's really easy to sample. What's nice about it is like, so what's cool about, so let's say, what's benefits of, I'll say Markov chain sampling, or I'll call this sequential sampling. MCMC. So one of the cool benefits of this is that you can sample from like any distribution you want without ever actually having to calculate the normalized distribution. So I'll just write that down here. So sample from distro without having to calculate normalization constants. Now, what do I mean by that? What I'm saying by that is you'll often in computational modeling want to build a model where you'll know that some agent or whatever is going to be in one location 5 times as likely it'll be in another location, and 3 times as likely it'll be in another location, and all these sorts of things. You can build a model where you keep track of all of these relationships. But if you were going to use a standard Monte Carlo method, then in order to draw from all of these possibilities, you'd have to take all of that stuff up and then sum them all together to figure out kind of like what the right normal, the thing is you want all the probabilities to add up to 1. So I might know that the probability that I'm in this location is twice as much as the probability that I'm in this location, but I don't actually know what the actual probability is. So in order for me to calculate, do I want a 10% probability? And let's say I said it's, I forget how many, say 5 times. So if I wanted 5 times the probability here than here, then do I want this 10 and 50? Do I want this 20 and 100? Do I want something else? Do I want this 5 and 25? I don't actually know what the raw absolute probabilities are. And in order for me to do a standard Monte Carlo, where I just take a sample from a solid distribution there, I would need to normalize for all that stuff. But in order for me to, all I might know in my physical modeling of the system is just these relationships. So in order for me to, before I can even do the Monte Carlo sampling, I have to actually then imagine what are all of the possibilities of things that could happen in the system, and then somehow then calculate, like if I were to add up all of my kind of things that are proportional to probability, what number do I get? And then divide by that. That was like the partition function. So like if you are familiar with using softmax in neural networks, you get these numbers that come out of your neural network that are proportional to or related to how likely it is that, you know, you get a bunch of, like, you show a picture of a cat to a neural network and it has outputs for cat, dog, chair, whatever. And then each one of those outputs is going to have a number, which is going to be a weighted combination of all the features in the image, which might be related to being a cat, dog, chair, etc. And if you show it a cat, then hopefully the cat one will have a large number. But in order for you to make sense of this, then what you typically do is you run those numbers into an exponential, just like in this kind of Boltzmann, and then you add up all the exponentials and use that as a normalization constant that divides each one of those outputs so that the probability across all the possible outputs adds up to 1. And that's what you do in the so-called softmax function. So you need that partition function, that normalization to do that. What's cool about Monte Carlo sampling is that you can sample from distributions without having to bother with that, because this ratio here gets rid of all the normalizations. So all I need to know is how likely how two states relate to each other and not relate to all of the states simultaneously. And so computational models typically like to use these these Markov Chain Monte Carlo methods because they allow you to build these relational models without having to actually go through the ugly work of calculating the actual probability distributions properly normalized. Similarly, if you've ever worked in Bayesian statistics or taken a Bayesian statistics course or whatever, you might be familiar that, like, these are great for Bayesian statistics for the same reasons, going from prior to posterior, prior distros to posterior distros, because very often when you are worried about in the Bayesian statistics, you would ideally you want to you give it a bunch of distributions for where you think things are. You give a bunch of new data, and then the Bayesian statistics updates your distributions, your prior distributions, turn them into a posterior distribution, and the math to make that happen, to spit out this posterior distribution, at the last step of that math, you very often have to do that same normalization process that I was just talking about. But the beauty of MCMC is you're not actually spitting out a distribution, you're spitting out samples. So you end up taking a histogram from your Markov chain, and that histogram is naturally normalized without you having to do any extra work. So these MCMC methods output histograms instead of bothering to normalize. And that histogram will naturally so it takes a lot of the computational effort out, because you're just sampling. You're not actually trying to calculate the actual structural form of it. But you can still get it, because once you get the histogram is going to be of the right shape. So these MCMC methods are beautiful because they focus on the shape of distributions and not the actual absolute numbers that go into these distributions. The downsides is that samples are not independent. In other words, what I mean by that is if you sample from a microstate that's here, the next microstate that's going to come out is probably going to be close to this microstate. Over 1,000 microstates, I'll get the Boltzmann distribution. But over 2 or 3 microstates, then I'm going to get, it's like a random walk. I'm going to get a microstate close to the previous microstates. So a lot of times when I want to draw random numbers, I really want there to be no way to predict one random number from the next of it. So if I really want to draw from the Boltzmann distribution, maybe it's important for me, maybe I'm doing some cryptography thing or whatever, and I really want that my next sample to be independent of my previous sample, but I want all the samples to come from a Boltzmann distribution. Well, the only way I could do that with the MCMC is to draw a whole bunch of samples and then permute them by some other means, and then draw from the permuted list afterwards. So, so you lose independence with these methods, but you gain a whole lot. So that's kind of a quick background on Monte Carlo, on Markov Chain Monte Carlo. Now, now I want to at least, show us the final simulated annealing algorithm that makes use of these Metropolis algorithms here. So that's what I'm going to do in the last couple minutes here, and then we'll shore that up at the beginning of next lecture. And then as we move into the next unit, which is completely different, the next unit where we start talking about swarm intelligence and where we actually put agency on these methods. So right now these microstates are dumb, they just jump based on energy. And then in the next unit, we're actually going to talk about agents that kind of make their own decisions, whatever the heck that means. But I want to, finish that up, and we'll probably shore it up next time as well. So, but are there any basic questions? So this isn't a question about MCMC, but I just wanted to give you an idea that if you're not familiar with Bayesian methods or MCMC, at some point in your professional engineering career, you will see these terms. You will have to use these terms, and these terms come from things that were inspired by thinking about simulating physical systems. So how do we get a Boltzmann distribution? We're going to try to simulate what might go on inside a chair. And then once we can simulate how do you get a Boltzmann distribution, well, heck, you can now use that as inspiration for how you simulate any distribution. And there's all sorts of neat benefits by simulating it that way, because this fancy ratio, the physicists recognized this a long time ago. Physicists hate calculating partition functions, and so they base a lot of their physics on this ratio of Boltzmann's. And that gets rid of that Z function, that thing that's in there. And so that's what the MCMC people do too. Right, so that's kind of history of how those methods can influence MCMC, but then we can end up actually going back to the standard Metropolis to talk about our simulated annealing. And that's where we'll close today. But any questions? You see anything online? Nothing new there. Okay, all right, so let's see a snapshot then. All right, so in 1983, Kirkpatrick comes along. I think I got Kirkpatrick's name right there. So Kirkpatrick et al. And this actually was a paper that showed up in Science. So rarely do you see algorithmic papers show up in Science, of all places. I mean, Science, of course, has Science, also a magazine. I mean, sell advertisements. So not the typical place that algorithms land, but it was pretty influential, and people thought it was pretty cool. So the paper that showed up there was optimization by simulated annealing. And so there were sort of, Kirkpatrick mentions, and I think we'll talk about this in the concept check for this unit, that there are 4 ingredients that are needed for simulated annealing to work. And that's a concise description of the system. It's basically your optimization objective. A random generator of movements or moves or rearrangements. So we're going to randomly move and kind of see how this comes. A quantitative objective function, so that's the objective function, and an annealing. So, sorry, the concise description of system, we can view that as kind of like a genotype. Like those are your microstates, your high dimensional view of the system. The random generator to move from one state to another. The quantitative objective function, the thing we actually want to minimize, and a so-called annealing schedule of temperatures and lengths of time. And that will be trial of error for a given problem. So we've already kind of outlined roughly how this is going to work. And so the basic idea here is that our decision variables are going to be the position and momentum of atoms, if you will. We've got the solution is going to be, so the solution is going to be a combination. So I guess what I should say here, you can think of sort of the position, momentum. These are kind of like individual variables. So you can think of genes and alleles. And then the solution is the combined configuration and so you can think of this as a vector, which is like a genotype. If we're thinking in terms of genetic algorithms as our conceptual model, the fitness we can think of as the energy. So these are all the kind of physical analogies over here. And so we're going to be minimizing energy instead of maximizing fitness. Our initial solution is random, and it's a single solution, not a population. And our process for generating new solutions, that is going to be the movement of atoms according to Metropolis for a given temperature. All right, and I'm probably gonna leave here, but just stick me for 30 seconds here. There were a lot of questions in the muddiest point about trying to anticipate simulated annealing and trying to understand what the hell is a temperature in terms of an optimization problem. And that's what we're talking about here. Temperature is a physical analog for us saying this is a budget you have of backward moves. And so we're saying that we are going to do a search over an optimization objective. We will always permit moves down because we're minimizing, but we're also going to permit some moves up. And the temperature is going to end up being our budget for how far you're allowed to move up. So knowing that we want to minimize the objective, there are going to be some moves that actually increase the objective away from minimization, but we're going to permit those because we know that sometimes you need to move up in order to get over a hill to come back down again. And so that's what temperature is. It's a budget. And what we'll see next time when I actually then write out the algorithm that uses this, which is really simple actually, is that we are going to start with a high temperature, which is going to mean you can choose any microstate you want. And then as we lower and lower the temperature, it's going to say that you can't move very far from your current microstate unless it's moving down. You can always move down, but if you want to move up, you're going to be limited by our temperature budget. So that's what temperature is. It's a movement budget. That's what it is in the physical system, and that's what it'll be here in this system too. That's all I've got for you. I don't want to keep you any longer, so I will see you on Thursday. We'll finish this up and then start talking about swarm intelligence. All right. right, so if there's any other questions online, I can take those real quick. Otherwise, I'll be closing the meeting. All right, in that case, we'll see everybody Thursday. Have a good week.